Classical Physics Tutoring, Chapter 5, Section 4, Magnetic Field Energy and Magnetic Force. Now, we did this for electric field energy. Exactly same symmetric relationship exists for the magnetic charge generating the field. Okay, so basically what we get is this equation, and the same as E d volume. Okay, so there is a field, and D, they depend on the dielectric material within the field. The same thing, the permeability affect this. So it's a symmetric equation for the field generated by magnetic charge, which is like you have magnetic charge. Okay, and so basically it's the same. Either you take a magnetic charge and potential to distinguish this from electric one, we put the M. So if you have a M or low M charge, it's generating magnetic potential, which is phi M and R, right? Okay, so that's a field. It's generated. It's going to have H and B, and they disagree if there is a magnetic material somewhere, right? So when there is a charge, it generates the field. The field contains the energy, and it's a little bit different. The difference is the true charge. We bring delta law against this electric force, and that was a work. Okay, but actually we can do same. It's slightly different here. You have to notice that the increasing M means it's M going. Increasing this M is going to increase how much energy. So physically the work is to increase M, and increasing M is not like moving magnetic charge all the way here. It's increasing by spinning some of magnet within the body. Okay, but that's the physical details, but mathematically it's exactly same calculation for the energy. Then how about the force? Well, there's no Coulomb's law for magnetic charge, but magnetic charge, they interact each other by force, right? So this is kind of magnetic Coulomb's law. Okay, so what it is you have a magnetic dipole in the middle, and far away you have another magnetic dipole. How do they interact? Okay, assuming that this distance R is large enough than L, I want you to go through this equation, spending time. We will get this equation. You set the Y and Z, then this is the force on each direction. It's more complicated than Coulomb. The Coulomb's just is attractive or repulsive. So magnetic force the first you calculate how much magnetic field generated by this dipole, right? And you combine this together into the vector format. This is the equation, okay? And m is this dipole's moment here. Okay. Now, what happened is, this is m1 and m2. It's going to have a forces. Actually, it's a torque. It's not like we calculate torque. Okay, it's not like attractive or repulsive. The torque, just simply multiply this. It becomes symmetric to m1 and m2 because this guy causing a torque to this one, so they are causing torque each other. Okay. And now, how about force itself? When you have this kind of generate, magnetic field, look like that, right? And this guy is gonna move along this line, right? So this is force to move. It's more complicated, but that's gonna be this. And this is a little bit more complicated equation, but it's very useful to solve some of the problem. I created several YouTube videos you can look at for the example question how to solve using these equations. Okay, so you should look at the video to practice this. So this is basically magnetic force, magnet to magnet charge. How about the magnet to electron? Then if you have an electric charge and it's moving in the magnetic force field, the electron is going to move, right? And you know this already. So this is something new. We never covered this in the electric field theory. This interaction is very 3D. It's an orthogonal force to the field. So we use to figure out Coulomb's law using potential. And this scalar potential was good enough for that. But we prepare one thing. We use vector potential. And potential can be vector. Yes, the vector potential is just like a scalar potential. We created mathematically for the convenience of calculating electric field or magnetic field, whichever. Okay, so the before scalar potential was defined this way, right? So we defined exactly same way, except this is multiplication, the outer multiplication of the vector. So the result is vector, and this is still potential, but the vector potential. Why do we need that? Well, let's use it. Okay, divergent B is 0, so B is curl A, and this one you can prove that this is one of Maxwell's equation, and the curl B is a curl A. You go through this manipulation, we get Poisson's equation. boy, Poisson's equation again, using vector potential. Remember, we had a scalar potential. This gave a Poisson's equation, which is right, and now we have a Poisson's equation, and the source of the vector potential is caused by current density, not the magnetic charge. Of course, we have magnetic charge, scalar potential. Okay, so these are symmetric. Now the current is more complicated in a sense that it's a 3D orthogonal direction. So it's going to be vector potential Poisson's equation. This is the vector Poisson's equation. And a lot of mathematics required here, and this is all about mathematics in this section. To understand the physics formula, you can just take the result after mathematics manipulation. You look at the result, but you need to understand the fundamental meaning of that formula, how it came about. Okay, and that's important to understand and use the formula correctly. So you need the understanding of where the formula comes from, what is the underlying fundamental claims it's making. Okay, so the we modify this, since it's a Poisson's equation, we use the same Poisson's integral format. Now, this is the vector potential integral format. You have I, current, and L. L is any current going through. This is a dl. And you take integral, path integral from A to B, and in this case, you need to have a loop to get this vector potential. Okay, now from here we can the B equals curl A. This is equivalent to E equals the curl A is, right, the gradient phi. It's this, right? So using this curl A, since we have a vector potential, remember the sequence, we define the potential, and from potential we got electric field, right? So once we get the potential, vector potential, taking a curl, we can get the magnetic field. Okay, so what's good about potential is the meaning you can attach energy, but that was scalar potential. Vector potential, there's no vector energy, so it's not energy, it's a mathematical quantity convenient to use to solve the problem. And that's a potential actually. Okay, and using that we get this, how the electric current element generate the field H, B, or H. Okay, and this lead to the Biot-Savart theorem we introduce later. But let's see. So that's what it is. Now we have a now we move to the Lorentz Force. It's quite more mathematical than any other physics books here. You have to bear with me because the real meaning, where the Lorentz Force come from, we can derive from the Maxwell's equation. So this Maxwell's equation, the integral meaning, integral format is this, right? Remember? And if you use this, you become this, as we already cover here. Okay, so you still have dt, and this is Maxwell's equation. So here's the thing. So physically, you have this electric field generated by the change of magnetic field, and magnetic field, actually is coming from the J current density, and this electric field is going to interact with electron. So this is what it means. There's no such a thing like magnetic force. Magnetic force is just intermediate interpretation of the phenomena. Okay, all the force, fundamental force is Coulomb's force, the electric field pushing this electron. And magnetic field, if you change, it's generate this electric field, and this electric field is gonna provide a force to the electron. This is basically interaction between electron and magnetic field, and this interaction is called Lorentz force. So Lorentz force is nothing but Coulomb's force, but this Coulomb's electric field is generated by magnetic field change d over dt. Okay, and this magnetic field is generated by what? Current. So the current generate magnetic field. Magnetic field generate electric field. Electric field basically use Coulomb's force to move the electron, and that's we talk about magnetic field provide a force to the electron, and that force is called Lorentz force. But it's nothing but just Coulomb's force. Okay, this is fundamental things you have to understand in the physics. And now, then what is a change on the magnetic field? Okay, you take this, the derivative of integral, and now we did this for the fixed boundary. This is a fixed boundary. Okay, but what if its boundary is not fixed? This is also time function. That's where the Leibniz integral comes in. Leibniz integral is a boundary change, and physically what it means is, well, you have this boundary and magnetic field going, and this magnetic field is a time function. For example, you move the magnetic stick in and out, then field change, it's called current, right? Okay, but what if this boundary is also changing time function? Say this ring is expanding or spinning, it comes into here. So actually this derivative integral has more terms, which this part is, you know, that's here, and Maxwell's equation shows only this part, and there is other part. ugly part, which is geometry related part. Okay, so we use d over dt integral potential field, and this potential field derivative is going to be this way. So using this, with the help of potential, the vector potential, we will get actually electric field generated along this line is going to be time variant magnetic field and moving effect. Say this ring is moving at the V, right, in the magnetic field. So the B is already time variant, but because this ring is moving, there is additional term, and that's what it is. Okay, and this moving effect is a cause of Lorentz force. You got that? Because this generate electric field cause Coulomb's force, and that's what it is. How much electric field is generated by moving V inside magnetic field V. So here you go. We just calculate the Coulomb's force for the electron moving inside a B at the speed V, and that's the meaning of Lorentz force. Okay, so you have a two force. There is direct force from electric field existing plus the electric field generated, which is this part. Together makes entire Lorentz force. For example, when you have a B and the electron moving in orthogonally, so you get the force toward the center of the circle. The circle becomes smaller and smaller. Okay, so that's the Lorentz force. And now I already said that from the equation above we get Biot-Savart Law. This is very useful because you can calculate from current to magnetic field, and this equation comes from here. Here. Okay. So you have to go through the, if I explain every detail of the equation, it's going to be like probably this 2-3 weeks class. You see all the overview here in this video, so that when you take the physics class in school, so you know what you're doing and you understand the meaning, where it's come from. You can all relate it and connect the dot together. Okay, that's the purpose of this video. Okay. Now, so you have your favorite Fleming left-hand rule, right? So you know where it's come from. Okay, the dialect come from here, but you're in college. You use the derivative element. Okay, so you're ready to take an integral to calculate. So you can say f equals I B kind of things, the high schools, but you have to take a derivative to calculate the not straight wire or circle or whatever. So this equation is basically used for designing motors, right? And a simple motor is a DC motor. You apply DC voltage to the wire, and you put the permanent magnet on the both sides to generate the B. Okay, so the current, the length of this, and B is going to generate a force. And what's happened is it's become vertical, right? And stop there. So what you do is here one side goes to this way, another side come from this way, right? When it's flip to the vertical position, then the nose is configured this way. So as soon as it's a flip, it suddenly switch the current. So it start moving again until it's become vertical. Then when it's become vertical, this side, this metal, the way it's contact is going to switch again. Okay, so this is a kind of a contact design for the DC motors. Each time it's a spin, for example, initially metal is like this, okay, and when spin more, it's going to be and when spin more, it's going to be non-contact. So the current is cut off, but you have inertia spinning, so it's come back to this again and repeat the same thing. So that way you can change the current direction at the vertical position of this coil, and that's why it's keep spinning around. Okay, think about this. This is a motor design. It's a DC motor. It's the simplest motors. And now the electric car use more sophisticated. They have many magnets. It's a DC motor, and the wire is configured in many angles. So when it's move a little, then contact is distributed. The current direction switch. This one switch, this one switch, this switch. So it's a give a kind of very uniform moment, power, the force. Okay, so this is kind of a improved version of DC motors used for the electric car. So you have a multi-phase, not just one side, from one side to other side, and the single coil moving. You have multiple coils. Like that. Okay, so that's the end of this magnetic force and energy. I hope you enjoyed this video, and if you like, subscribe.